Welcome to lecture 20 on risk management and insurance. So far, we considered an insurance company with a given number of clients. For example, we looked at the benefit fund with 1,000 members. So the insurance company had sold 1,000 insurance contracts and that number was fixed. Now, here we will now relax this assumption and the insurance company may decide on the number of the insurance contracts that it will sell. So it will decide on the volume of its business. N will indicate, the number of insurance contracts that the insurance company sells or underwrites. It will be shown that an insurance company can reduce its risk by expanding its business if claims are independent. So when the insurance company sells more insurance contracts, actually its risk will decline. And the idea is very simple. The insurance company just simply will spread the risk over more clients. Now, car accidents are independent, and the same holds for today for house fires. In the past, actually, it may not have held for house fires, as for example, during the Great Chicago Fire in 1871, when basically the entire city burned down. Now, the drought risk of farmers is different, because a drought actually may affect an entire country or even a group of countries. In health insurance, both may apply. So most illnesses will strike individually, just a single person, but there may also be an epidemic, as now with the coronavirus crisis. So health insurance, maybe the losses are independent events, but they may be also related as during the coronavirus epidemic. Now, drought risk may affect a lot of farms or maybe an entire country, and that's a major problem, in agricultural economics. So what we do in this chapter, we will look at the situation when the risks are independent. So the insurance company sells a lot of insurance contracts and the risks that it makes a loss on those contracts are independent. Let's first look at the weak law of large numbers. The weak law of large number considers the deviation of the sample average from the expected value. The expected value is just the mean value. And I'm using here actually the symbol mu. I do not use E of x, for the mathematical expectation. So let's consider a random sample, x1 up to xn. The weak law of large numbers states that the probability that x bar, that the sample average deviates from the mean, from the expected value, that this approaches zero as n goes to infinity. So the probability that the sample average deviates from the expected value or mean approaches zero as n becomes larger and larger. And that's usually written down like this. So you have here the sample average, you have the expected value here or mean, and you're looking at the difference. And this difference, as n goes to infinity, the probability that this difference is bigger than arbitrary small value is actually equal 0. So x will move toward mu. X bar will move toward u. The probability that the sample average deviates from the mean by an arbitrary small number epsilon, that probability, okay, approaches 0. That is the law, the weak law of large numbers. You can also write it like that. So the sample average approaches the expected value when n goes to infinity. And another notation is this Bling notation that you find sometimes in a econometrics book. The probability limit, okay, approaches of the sample average approaches actually the expected value. Now you can prove this using the Chebyshev inequality. It's actually quite a short proof, and maybe you look it up on the web. So what's very important here, and which what actually sometimes creates causes a little bit of problems with students, is the difference between the average, the sample average, and the expected value. You see, the sample average, that's what we observe. The expected value, we don't know. The expected value, or this mean, that's a so-called population parameter. That's an underlying population parameter that we cannot observe. So we do sampling, we calculate the sample average, and then actually we are interested, is this sample average that we observe, is it really related to the underlying population parameter, mu, okay, the mean or expected value. Now the weak law of large numbers says, okay, that actually when the sample gets bigger and bigger, then really the sample average approaches the population mean. Now, why do we call it the population mean, this parameter? That actually has historical reasons. In the 19th centuries, the statisticians actually did studies on the population of England. And so they would have, for example, they wanted to know what is the average height of a person, of a male person or female person in England. So that would be the population parameter. They are interested in the population parameter. And they did not want to measure everybody, so actually they just sampled. So they looked at the sample mean, at the sample average. And then actually, because of the weak law of large number, if you make your sample bigger and bigger, then actually this sample average will approach the average height of people in England, of the entire population. Now, in England, naturally, you could have measured everybody, but this just would have been very expensive. That's why they only did the samples, and then really took the sample average. Maybe they took quite a big sample, but they did not want to measure everybody. Now, the population can also be infinite. So, for example, if you would like to know what is the average value you get when you throw a dice. Okay, what will it, so you just throw the dice many times, and okay, it will actually approach the value 3.5. That's the underlying parameter, okay, which you can call the population mean, which would be called the population mean, just for historical reasons. Now here you would actually deal with an infinite population, because actually you can just throw the dice an infinite number of times, and so then you're really forced to use a sample. So it makes this very important distinction between an observed sample average and the underlying parameters that we would like to know, okay, which is actually the population parameter. And it's called population parameter just simply for historical reason, because actually those techniques were developed by demographers in England in the 19th century. They studied the population of people living in England. Now let's look at the insurance relative risk. The insurance relative risk is the risk that claims will exceed expectation, will exceed the expected value. So it's a risk that claims on average will exceed what is expected. That will exceed the population parameter. Now let's consider an insurance company that holds a portfolio of N risk units. So it has actually sold N insurance contracts. And let's assume now that those risk units are independent and identically distributed. Now they are so-called IID. That's a notation that's used in econometrics books. In that case, okay, each loss from each risk unit has the same expected value and the same variance, and the covariances will be 0. So we assume, okay, that the losses from the different insurance contracts are independently distributed and identically distributed. Okay, so they are IID. So they all have the same expected value, the parameter mu. They all have the same variance, and also the covariance is assumed to be 0 because of independence. So the average loss per client is given by equation 18. So you have the loss of each client, and then you divide by the number of clients, you get the average loss. Now in the sample, naturally one client may have a big loss, the other client may have a lower loss in a given year. So you just divide by N, the number of clients, and you get the average. And you can actually calculate the variance and standard deviation of this average. Now just apply, okay, the sum formula for a variance that we have looked at in an earlier appendix. You see, we have here a sum of random variables, and actually each random variable is multiplied by 1 divided by n, and the random variables are assumed to be independent. So really what you get here is just a variance of the first random variable plus a variance of the second random variable plus the variance of the third, and so on up to the nth random variable. You multiply each one by n divided by n squared. Remember, with the variances you have to square this. And since this goes up to n, okay, so we can actually use n here. We have here n items, and each item is constant. You see, we have always the same variance here. That's by assumption. That's because those risk units are IID. So you just can write it n, and so the n factors out, and you get this here. And here you also have the standard deviation. So that's naturally a very well-known formula, okay, for the standard deviation of the average in a random sample. Now let's apply this to the weak law of large numbers. So let's assume this epsilon that we had here let's assume that this epsilon is k times, okay, the standard deviation that we just have calculated, the standard deviation of the average. So the insurer's relative risk consists of the possibility that the average loss exceeds the expected value mu by more than k standard deviations. So here we have k standard deviations. So the relative risk is the possibility that this average loss here exceeds the expected loss here more than k standard deviation. Now we can plug in from equation 20 from before. So just use this here. So take this from equation 20. So substitute in, and we get this. And so you see, as n goes to infinity, in the limit, as n goes to infinity, the probability will approach 0 that x bar deviates from the expected value by an arbitrarily small amount of amount here, epsilon, which is given by this n here. That's now the epsilon. As n, when n increases, this here falls and falls and falls. So we have here, we can make this arbitrarily small by selling more and more insurance contracts. So the limit of the probability that x bar deviates from mu by an arbitrarily small amount when n gets bigger and bigger, that probability is actually equals 0. So here again, I just remind you that the epsilon is this here, and that gets smaller and smaller as n approaches infinity. And we can again write this, okay? The average loss in an insurance portfolio approaches the expected loss, or the mean here, as the number of risk units increases. And again, you can write here, it's the probability limit of the average loss as n goes infinity approaches actually the expected loss. It approaches the so-called population parameter, mu, the expected loss. Okay, so that's the insurer's relative risk. We have looked here actually at the average loss per insurance contract. We have here all the losses added up, and then we divide it by the number of insurance contracts, and so we get this average loss per insurance contract. Now when we move now to the absolute risk, okay, we do not look at the loss per insurance contract, we just look at the total loss. We do not divide here by n. So in equation 22. So it's a total loss here. It's not a loss per client or per insurance contract as in equation 18. Here it's the loss per insurance contract. We have divided by n. Okay, now multiply on top and below with n, and then you can collect those two terms here. Those two terms, so now again, the average loss. So the total loss is naturally the average loss times n. That's always the case. Now multiply equation 21 by n. So we go back to 21, we multiply by n, so we get the n x bar and minus m mu, and we have an n here. And n x bar is just ln. So for n x bar, I write here just ln. And then we have the n here, and we have the n here. Then substitute in again from equation 20 for the standard deviation here. Remember, the standard deviation is here sigma is actually sigma divided by square root n. Here we have the standard deviation of the average. So plug in here sigma divided by n, square root n. Now, so down here you have square root n, and then up here you have n. Now, n is naturally square root times square root. So one square root will cancel out, and you just wind up with a square root here on top. And so you see here actually, if n now goes to infinity, the probability that the total loss here, the total loss is different from the expected value by some amount, that actually does not approach 0. Okay, this does not fall here. This this actually becomes bigger and bigger. The difference between the two, the observed loss and the expected loss, that's becoming bigger and bigger because the square root is up here. So the total loss ln does not converge a probability to expected value mu. The two items here, the two terms here do not become equal as n gets bigger and bigger, because the square root here it actually will increase more and more. Now the next table shows the insurer's relative risk and absolute risk for car insurance using a threshold of k of equal 1. So actually that the loss deviates from the expected value by 1 standard deviation. K is just a multiple of standard deviations, and we just take a 1 here. We assume that the expected loss is 500. That's a population parameter, and we will never observe it. But we can calculate the averages of the sample. And the standard deviation is 800. So we have here the relative risk. Here we have the absolute risk. So when you go back to the formula from before, you see this here. This here measures the relative risk, that we are k standard deviations away from the expected value. So we have this here, and then here we have the absolute risk, and actually we work now with a k equal 1. So if the insurance company is small and just sells one contract, okay, then naturally the relative risk will be $800, just a standard deviation here. We divide by 1, okay, and we get 800. The same thing here, we will get just 800. Okay, 800 times 1, and anyway we assume that the k is equal 1. Now, if the insurance company sells 10 contracts, okay, so you divide here by the square root 10, and here you multiply with the square root 10, okay, you get this here. And if it's selling 100 contracts, okay, and so on. So you see here the relative risk which applies to each contract, it's falling. On each contract, the insurance company will actually expect the risk will be reduced. The absolute risk, however, will be increasing. So that's a total risk of the insurance company. And this here is a relative risk. So that's a risk per insurance contract. So it's actually, you see here, it's difficult to enter the insurance market. Maybe you're thinking about establishing an insurance company. Okay, at the beginning, your insurance company will be small. You will only sell a few contracts. Then actually the risk of each contract will be very high. The absolute risk will not be high, but the risk of each contract will be high. So it's very difficult to establish an insurance company. As the insurance company grows, then the risk of each contract gets smaller and smaller and smaller, because the risk is spread over more contracts. Naturally, the absolute risk will increase because the company gets bigger, okay, so the total risk will increase. So size is beneficial for the insurance business. An increase in the number of contracts reduces the insurer's relative risk. It reduces the risk of each contract. The absolute risk, however, will increase, but even here, the insurance company benefits because the premium income will increase with n, whereas the absolute risk increases with the square root of n. You see, when you sell more and more insurance contracts, naturally your income increases with n, but the absolute risk only increases with the square root of n. And so also actually here, the insurance company benefits. Okay, this has been the classical ruin theory. That's what I have to say on the classical ruin theory. So theory started at the beginning of the last century. Actually, 3 actuaries were important here. Remember, I spoke about actuarial science. Some universities have departments of actuarial science where they discuss insurance. And for example, the University of Cape Town has such a department. Now, Bachelier was very important. Okay, he applied probability theory, okay, in financial markets. Actually, he applied to the stock market. And his thesis, his PhD thesis, was actually supervised by Poincaré. Okay, it's a very famous French mathematician that you probably know. Now, Lundberg, he was a Swedish fellow. He worked on insurance and reinsurance. Now, Bronson, okay, he maybe is a little bit less important. He also used probability theory and tried to explain option pricing, but the prices of options. But he was much less successful than Bachelier. Bronson actually worked 8 years after Bachelier, but actually he was obviously not aware of Bachelier, so his models actually were not such good. Bronson had studied physics, and Bachelier, okay, obviously with Poincaré as a PhD supervisor, he was a mathematician. Now, we discussed classical ruin theory. Modern ruin theory actually considers the timing of claims during the planning period, which is a year in our case here. So it really actually also looks at whether an insurance claim occurs in January or maybe in August. So claims are then modeled as so-called stochastic processes, and we will look at this in a later chapter. It's a very active field of research, I must say, in actuarial science, ruin theory. Okay, but it's actually now with stochastic processes. Okay, that was the lecture for today. We have now finished up ruin theory, and next time we move to financial theories of the insurance company and insurance supply.